All right, we're back. We're going to be on page 125, but there were some calculator things that I wanted to show you involving this. And so I'm going to jump over and do that. So this is the bottom of page 124. That's where I'm going to be like pulling the examples from. And what I wanted to show you first was that the calculator actually has, unit vectors are so important that they're built in. Menu 7, option C. So press C or just, so if you press up a couple times, or just once really, it takes you there. Menu 7C, and then option 1 is unit vector. So unit vector, and then you have to give it the vector that you want the unit vector of. So remember, it's brackets, that's control open parentheses, and then do 5, 12, and it'll just spit it out for you. Other things you can do is you can scalar multiply. So if I want to do, so for example, I can take the previous answer and multiply by 13. It'll give me this. Or I can do one of the problems. So 14 times, so scalar multiplication is the same as matrix multiplication. Well, no, it's on the calculator, it's the same process, I guess is what I mean. So 3/5, comma, 4/5. As soon as you hit enter, it gets rid of the comma and it like puts it into a template. So like you could actually, I don't really think it's faster, but you could do like 10 times and then go into the templates and choose the 1 by 2, 1 row, 2 column matrix and just use that. So like -1/2 tab square root 3/2, and you get this. So these are all things that we're getting. There's some other stuff on the calculator that I'd like to show you, but I don't think now is the time, unfortunately. So I'm gonna go to the notes and start working my way through this page. So let's see what page 125 holds for us. So unit vectors are a huge, huge deal. So you always just take the vector, divide it by its magnitude, that's your unit vector. Once you have a unit vector, it really just tells you a direction. Like you're standing at the origin, face a certain point on the unit circle, right? Which means we could just say face a certain angle, which is the ideal thing. And then we know the ordered pair would be cosine of the angle, sine of the angle. It's like it's all coming together. So let's talk about these direction angles. But I'm telling you right now, we already know a ton about them. So direction angles. So we want to find the exact, so this is actually a throwback, the exact value of the angle passing through the given points. If you remember, we always use inverse tangent. And we always use inverse tangent because inverse tangent involves sine over cosine or y over x. It involves the things we were given. We don't have to calculate anything. So here, 5, 12, just want to make sure what quadrant I'm in. So I'm going to say that theta is going to be the inverse tangent of 12/5, and I'm just done. But the quadrant really matters. So here, -8, 15. Okay, so now I need to do second quadrant. Should we be in degrees or radians? I'm going to be in radians. I'm going to say that the angle is pi minus the reference angle, which is the absolute inverse tangent of the absolute value. You don't really handwrite the absolute value part, but you use the absolute value, right? So the key thing is to make sure that you're doing that, right? So this is -8, but we used +8 because of absolute value. We just didn't show it. -24, -7, that's going to be here. So here, third quadrant, I'm going to do pi plus the reference angle, which again, I'm using absolute value, but in this case, y and x are both negative, so it wouldn't make a difference. And then finally, 20, -21. So 20, 21, 29 is a triple. Doesn't matter. We're not using it. Actually, all these are triples. So I guess that's to like, I don't really know. So one option here is to say 2 pi minus the reference angle. But like, that's not the most efficient way to get there, right? So if I do 2 pi minus, then what I'm doing, like here's my, this is like super close to a 45-degree angle, I guess, because its tangent's like really close to 1. For this, I'm doing this, right? 2 pi minus the reference angle, not very efficient. Or let's swap up the color on this. Or what we could do is more efficiently. So I'm talking about efficiency because there's something that happens with vectors that doesn't happen with the other things that we've looked at. And the thing is, with vectors, you typically do the most efficient thing. So it's not really efficient to go all the way through quadrant 1, 2, 3, and then a little of 4, when all you needed to do was go a little of the way through quadrant 4. You always want to do the most efficient thing. So that's a thing we're going to run into that we have not had to deal with prior to that. But all of these are called direction angles. So the definition of a direction angle is familiar. It's direction angle, so I'm calling it theta sub v. So it's the direction angle for vector v is an angle between negative pi and pi inclusive. So negative pi and pi are coterminal. So when you have to choose, you choose pi. And it's the angle formed between v and the positive x-axis. So it's all the stuff we've done. It's just that instead of saying 7 pi over 4, we're going to have to say negative pi over 4. Instead of saying 11 pi over 6, we're going to say negative pi over 6. You have to use the negative equivalent because you're not allowed to go over pi. So that's something we need to think about because you probably haven't thought that way before, but not really a big deal. So all of this is, in some ways, review. It's kind of weird. All right, so what are we doing? Find the exact direction angle. By the way, the more often you think, oh, this is just what we already did, the easier the course will seem and the better you will do. So anytime you see something that you think is something we already did, confirm that it is. Maybe look back in your notes, talk to a friend about it, ask in class, whatever. If it's the same, build on that. Don't just try to why would you try to build like two things next to each other when they're really just this being reinforced? There's no point. So here, find the exact direction angle and the unit vector. So I think it makes sense to find the unit vector first, because if I know the unit vector and if I recognize it as a unit circle point, I'm basically done. So I'm going to try to do that. Here, I look at this and I think, I see radical 3, right? Radical 3 over 2 is definitely on the unit circle. What would I need to do to make a radical 3 over 2? I'd have to divide by 24. Can't just divide by 24. So I'm going to bust out a trick that we've been using. I'm going to multiply this by 24 over 24, a clever form of 1. So this is going to give me 24 times 12 over 24, and 12 root 3 over 24 gives me this. So now I actually know that the magnitude is 24. That's the magnitude or the norm. And then I know that the unit vector is 1/2 radical 3 over 2. And I did that really because of the radical 3. Like I recognized radical 3 and I was like, oh, radical 3 is in the numerator of a unit circle point. So my unit vector is 1/2 radical 3 over 2. And then the direction angle, so I'm going to say it's like theta sub v. Well, what angle goes with 1/2 radical 3 over 2? That's pi over 3. Which means I can rewrite my unit vector if I wanted to as cosine pi over 3, sine of pi over 3. Like, do I want to do that? Yeah, I mean, I probably do actually. Like, if for no other reason, then it's really good practice at this point. And maybe there is no other reason at this point, but like, definitely that's good practice. So you should definitely do that. Here, I see another radical 3. Should be over 2. So what am I going to do? Well, if I multiply by 2, I would get negative radical 3 over 2. So I'm going to do the 2. I'm going to do 2 over 2. So I'm going to say this is 1/2 of, right? So the 1/2 is this 1/2 because I need to distribute this 2 to make 1/2 in the denominator. I hope that's clear. If it's not clear, by the way, you can just like find the magnitude of these and divide by the magnitude. It totally will work. It's just like if you already know what you're doing, like why would you do that? So this will give me a negative radical 3 over 2, 1/2. Another way to think of it is I just needed to factor 1/2 out of this thing. That's actually a better way to think of it, but it's not how I chose to think about it. Same with the previous one. Could have just factored out whatever. Here's my unit vector, and here's my magnitude. And so the magnitude is not really important in this, but our unit vector, we're just searching for unit circle points. Our unit vector is, holy cow. I don't know what happened there. Wow, different page, different everything. Okay, unit vector. I don't know what I hit. Negative root 3 over 2, 1/2. And then theta for this vector, the direction vector. So negative root 3 over 2, 1/2 is going to be 5 pi over 6, which means I can rewrite this as cosine 5 pi over 6, sine 5 pi over 6. So this is going to end up a very common way for you to write unit vectors. Like usually you're just told the angle. Like the direction angle is, I don't know, 7 pi over 53. And you're like, what? So if the direction angle is 7 pi over 53, then the unit vector is cosine of 7 pi over 53, comma sine of 7 pi over 53. Do we know what that is? Not really, but that's done. All right, let's see. This I'm going to do a little work on. So first, I'm going to say 7/2. I'm going to rationalize negative 21 root 3 over 2 times 3. Okay, I see where this is going, I think. So I'm going to take out 7 and have 1/2 negative root 3 over 2 left. So you can confirm that. Just try to work it out. So distribute 7, basically. And then what happened? 21 over 3 became 7. So we have this, and then we have our unit vector. So the magnitude is 7, and the unit vector is that. The magnitude doesn't come into play here. So our unit vector is going to be 1/2 negative root 3 over 2. Our direction angle, well, what does 1/2 negative root 3 over 2 go with? So ordinarily, I would think 1/2 negative root 3 over 2 is 5 pi over 3, but I'm not allowed to use that. 5 pi over 3 is not between negative pi and pi, so I'm going to go with negative pi over 3, which is probably the weirdest part. And it's just because we're not allowed to use it. So we didn't get to make that rule. And that's like totally fine. Like we didn't need to use their rule. Well, we didn't need to use what we wanted to. We'll follow the rules, not a problem. Okay, so we got that. All right, I'm gonna do one more and then I'll come back in the next video and finish this and also show you some calculator stuff because I think the calculator stuff is really useful on this. This one's weird because if I'm just gonna take out 19/3. And then what am I left with? I'm left with 0, negative 1. And so that's a unit vector. This is a unit vector. And then this is the magnitude of the vector. And so like, what is that pointing at? That's pointing at the negative y-axis. So my unit vector is 0, negative 1. The magnitude is 19/3, but again, it's not relevant to this problem. So like, whatever, it's just kind of, scalar multiples are just in the way usually. And then we want to say 3 pi over 2, but we're not allowed because that's not between negative pi and pi. So instead we'll say negative pi over 2. It might be helpful, by the way, to sketch them, to sketch the actual angle, right? Like for this one, like you wanted to go with this, but you can't. So you're like, oh, negative pi over 3. And on this one, you want to go, so like here, we wanted to go all the way here, but we're not allowed to. And then for this one, we want to go here, but we're not allowed. So we actually just go this way. There's 2 ways to get to any, well, there's an infinite number of ways. There's 2 directions you can go to get to any angle. All right, so I'm gonna stop this here. I will be back in the next video. We're gonna do some calculator stuff and finish this page, and I will see you there.